All right, so the first thing we're going to do is find all the allowable quantum numbers. Before we start, let's talk about what quantum numbers we know. So because it's a 3p, we already have some information. The first is that n is equal to 3. Okay, the p tells us what L we have. Can you tell me what L we have? Someone said 1, which is correct. So just to remind you guys, we have options, 0, 1, 2, 3, 0 being S, 1 being P, 2 being E, 3 being F. So the allowable ones for this one are 0, 1, and 2, which can be n minus 1. But this one we're already given is P, so it has to be 1. So now let's talk about allowable quantum numbers. So these essentially were given as soon as we were told it was 3p. The allowable ones we can talk about are m sub L and m sub S. So first let's talk about m sub L. M sub L, just to remind you guys, can be negative L all the way to positive L with 0 in between. So m sub L is going to start at negative 1. What are our other two? Yeah, 0, 1, exactly. So these are the allowable ones. Now let's talk about m sub S. M sub S only ever has two values. One is negative 1/2, and the other is positive 1/2. So the allowable one for this one is just negative and positive 1/2. Yes? Sometimes it will be given, but it'll just be, they'll either tell you it's negative 1/2 or positive 1/2. Or sometimes they'll say it's a spin answer, so then it'll be positive. Okay, so now let's draw these. So it's a p orbital. So the easiest way to draw them is to just make an axis and label it. So this is our x-axis. So it's going to have this shape. Then we have, so this is p of x. Then we have p of y. It's going to look the same. The only difference is I'm labeling this as my y-axis, so I know that the lobe is going along the y-axis. And then lastly, we have z. So this is dy, p of z. So when we're given the wave functions for 3p, it could be any of these three. It's not specified. This would be m sub L negative 1, m sub L 0, and m sub L positive 1. So since there are 3 m sub L's, there should be 3 different orbital shapes. Or actually orientation. Same shape, just different orientation. Yeah? Oh, yeah. Okay, so now let's talk about the nodes. I actually didn't draw this completely. I didn't draw this completely correct. There's a radial node right here in all of them. There's also an angular node. The angular node just goes like this. It's pretty much in the, along this axis, along this plane, so that no electron can cross this. So how do we know that we are going to have an angular node? Well, whenever your L is greater than 0, you're going to have at least one angular node. So L of 1 angular node. L of 2, and etc. Now how many nodes should we have total? Well, n for this is 3. And the number of nodes is equal to n minus 1. So we should have had 2 nodes. And for each of these we do. We had our 1 angular node and 1 radial node. So that adds up to 2 total nodes. So we know that we found all of them. Okay, so any questions on this? Yeah.
On the first P of x divided P to 50, how do you know which one is negative, one, 0, and 1?
So I should say that is arbitrary, actually.
Okay.
So it's arbitrary. You just need to know that each one corresponds to 1.
Gotcha.
We could have changed it. Okay, now we're going to find the wave function for so this is 3px. So one of the nodes we were just looking at. So you won't be expected to memorize this, but you will be able to look it up. So every node has 2 components. We have a radial component and an angular component. So now you have this in your reader, you'll have it on the back of your exam, you'll have all of the radial and angular nodes that you may need to look up. So we're just going to look these up in the table to fill in what we know. So, consider this one. So we're looking for, we'll find the radial node first, we're looking for the 3p, so that would be this one right here. So now I'll just transcribe it to our sheet. That would be 1, 9 over 6, d over a naught, 3 halves, 4 minus sigma, sigma times e times sigma times e to the negative sigma over 2. And we know that sigma is equal to 2zr over a naught. So this is a very complicated equation, so you shouldn't be expected to memorize it, but you do need to know where it comes from and how it's used. So sigma we're just going to leave as is. That's a variable that's very convenient. It's a function of r, the radius. So a radial function is a function of r that we expect. For this, we're not given the element, so we don't know what z is. Z is the charge of the nucleus, so the nucleus does play a role in how the radial function looks. We don't know what it is for this one, because we need to know z. And then a naught is just a constant. So we're going to multiply this by the angular wave function. So again, we're going to look it up. We're usually going to use the spherical one. So we're going to look up y equals px right here. That's going to be times 3 over 4 pi to the 1/2 times sine theta sine phi. So this is the radial function, or this is the wave function for 3px. That's all you're going to be expected to be able to know how to do for this. But you should know that what this describes right here, this whole big long function, it's very complicated, is it describes this shape. So this shape is perfectly described by this. It's a very complicated function, and wave functions for electrons are complicated, so this is expected. But this, they're the same thing. So are there any questions on that? Oh, thank you. Yes, I wrote the wrong one. Cosine p. Yeah, that was for p of 1. So then one thing just mentioned, like an aside right now, is before when we were talking about atoms, we said things like, this is what an atom looks like. Where this is n equals 1, this is n equals 2, this is n equals 3. This is fairly incorrect because the actual shape is much more complicated. Electrons don't behave in spheres for the most part. Maybe the s orbital does, but the p, the d, the f are all very complicated. So what you actually get is you have your nucleus right here. You have maybe one electron in this 1s, and then another one in this p orbital. So the shape of electrons is actually very complicated. That's why we're spending so much time on this. because this is essentially fairly inaccurate. It's very, very approximate to the point where we can't use it. All right, so now let's talk about electron configuration. So last time, you guys finished on writing out the 4 different types of electron configuration. The first one you got to was S, P, D, F, condensed. So the example I think you guys had was carbon. So if you look at carbon, the best way to do it is use the periodic table, which we have right here. Cool. So 1s, 2s, or 1s1, 1s2. And then we have this right here, 2s1, 2s2. And then where carbon is right here, so it's 2p1, 2p2. So we just go along the periodic table, putting down electrons. So this is the condensed. This is what you guys saw last time. Now we're going to talk about the SPDF expanded. So it's very similar to what we just did, but now instead of grouping all suborbitals together, we're going to expand them. So S's don't expand. There's only one orbital that fills up with 2 electrons, so that stays the same. What does happen, though, is the p orbital, as you know, has 3 different orientations, the -1, 0, 1, or x, y, z, right? So we're going to expand this as 2px1, 2py1. Because one electron is going to sit in the x orbital, and one is going to sit in the y. We'll talk about why they're not both in the x orbital in just a second, but just suffice to say, this is how we would expand it out. So most often you're going to use the condensed, or you'll use the next one I do, which will be the orbital diagrams. So any questions here? We'll talk about orbital diagrams. So in this version, we're going to draw everything explicitly. So let's talk about carbon again. So we're going to have our 1s, our 2s. Now we're going to expand the 2p into all 3. So this will be x, y, z. You don't need to label the x, y, and z. I've just done that. So now we're going to fill it up. We fill one orbital at a time. So first this one, then this one. Then next we're going to go up, up. So 2 things to notice here. One is I didn't fill up both of the x's. I filled up an x, then a y. That goes back to Hund's rule, which says that electrons don't like to pair until they have to. So electrons fill orbitals singly first. So they fill up each one of these single, and then they double. So as you saw when I filled this up, I filled up 1s, then I doubled, because there were no other orbitals to choose from. Then it was 2s, 2s. But now when I have more than one orbital to choose from, I fill up each one before I start to double. So that's Hund's rule. The other rule is the Pauli exclusion principle. Is no 2 electrons have the same quantum numbers. So each electron should be distinguishable from every other electron. If they had the same quantum numbers, they would appear as the exact same electron. So right here, one was spin up, the other was spin down. That is so they had different quantum numbers. Because otherwise, it's n equals 1, L equals 0, M sub L equals 0. So unless one of these is spin up and spin down, they're going to be the same. So one had M sub S positive 1/2, the other had M sub S negative 1/2. So you'll never see 2 spin up electrons in the same single orbital. So any questions on this? So the last one we're going to talk about is the energy diagram, or energy level diagram. It's pretty much just like the orbital diagram, except we include energy. So we have E. So as we move up, we have 1s, 2s, 2p. So instead of using boxes, we use lines. It's just the way it's done. So we fill up the 1s first, then the 2s, and then now we're going to fill up one of the p and fill up another p. So the reason we fill it up the way we do is because 1s is the lowest energy. So you fill up the lowest energy orbital first. And then we have 2s, which is the next lowest. So we fill up both of those. And then lastly, we fill up the p orbital. Since the p orbital, the m sub l, -1, 0, and +1, all have the same energies, we fill them up separately. So we don't fill up all this one, then this one. We fill up one here, and then if there was a third electron, as in the case of nitrogen, we fill up this one. So let's do another one of these, because you're probably going to do one of these on exam or see them again. Let's go ahead and do fluorine. See that? Yep. So fluorine, it also has, first we'll do the electron configuration. So it has 1s2, 2s2, and if you look at the p, there's 1, 2, 3, 4, 5 p electrons, so it'll be 2p5. So now let's make the energy diagram. We have 1s, 2s, and then 2p. So we'll fill this up the same way we did before, starting with the lowest energy levels and then going up. So it's up, down, up, down. Now we fill this up, we're going to follow Hund's rule again. So it's 1, 2, 3, and then 4, 5. So we do end up pairing when we have enough electrons. So I should say this is an atomic energy level diagram. All right, no questions? So let's talk about what we, question? Actually, yeah. So if you were looking at an energy level diagram, which is not in the scope of what you'll be tested on, let's say it was excited. You might have that you have your 3s right here, and one of these electrons would be up here. So you wouldn't have this, it would look like this. Then you would know you've excited one from the 2, n=2 to n=3. Because there's an open spot. Not a long-lived electron configuration. Because it'll give off light as you can see. All right, so ions behave a little bit differently. So let's talk about O2 minus. What is the electron configuration for O2 minus? Well, we first talked about O. The electron configuration for O is going to be 1s2, 2s2, and if we count it, we have 4 electrons in the p orbital, so 2p4. Now, what is O2 minus? O2 minus is essentially just O with 2 extra electrons. So what we're going to do is just add those 2 extra electrons. So instead of being 2p4, O2 minus is going to be 2p6. So we just take the base electron configuration and we just add those electrons. Now what's another way that we could write this? What's special about this once we became 2p6? Yeah, it's a noble gas now. So when things become noble gases, it's often easier to write it as a noble gas. So we'll write it as neon. So O2 minus, as you can see, is pretty stable once you get to those extra 2 electrons. It becomes noble gas. All right, so now that we've learned all these rules for the off-bound principle and how to fill up electron configurations, we're going to talk about all the exceptions that exist. There are several. So the first one, and this is true for a lot of chemistry, starts with transition metals. So So as you know, when we move along the transition metals, we start to fill up the d orbitals after we filled up the 2s orbitals. But that's not the case for group 4 in the transition metals, so chromium and molybdenum, and also in group 9, so copper and silver. So these guys do not behave the same. So let's talk about the exception there. What happens here is the s orbitals don't fill completely. So let's look at chromium first. So we'll start with the nearest noble gas, which is argon. So as we fill that up, if we did it normally, it would be 4s2. And then we would have 1, 2, 3, 4 d orbitals, so 3d4. But this electron configuration is incorrect. What it actually is going to be is 4s1, 3d5. We have a similar thing for molybdenum, where we have this going to be krypton, 5s1, 4d5. So, do you guys have a guess as to why this is? Why we skip the 1s when we have 5 as a d? So the reason is because if we had 4, we pair the s, the 4s, but we have in our d, we have 1, 2, 3, 4 up. But in this case, we have 1 up, and we have a completely filled d. The d is not paired in all of them, but we have each orbital is filled with 1 electron. It turns out this is pretty stable, so because it's stable, we move 1 of the s electrons into the d configuration. So then if we look at copper, it's a similar thing. Copper is argon, 4s1, 3d10. So just remember when you're filling up 4 and 9 in the transition metals, you only fill up 1 of the s's. Okay.
When you go on to manganese or chromium, you can put that electron back in the S.
Yes, exactly. Yeah. So he asked a good question in case you guys can hear it. When you do the electron configuration for manganese, is that going to be 4s1 3d6 or 4s2? So let's write this out. Manganese, is it going to be 4s1 3d6 or is it going to be 4s2 3d5? It's going to be 4s2 3d5. So the only one with the 1 paired s is going to be the chromium and the copper. Not the except, though, when we start talking about ions. So, more transition metal. So before, when we were talking about ions, the example I gave was oxygen. We just added the electrons. Well, metals, because they're metals, like to give away electrons. Well, what happens when they give away electrons? So let's look at the example of iron. So iron, we draw the electron configuration, is Ar, 4s2, 6, 3d6. So that's iron. That is the correct electron configuration for iron. But what about iron 2+? Before, and in pretty much everywhere else, if you're talking about cations in group 1 and 2, or if you're talking about the nonmetals on the right, you would just take off electrons from the one that you just added. So in this case, it would be D. But that's not the case with transition metals. Transition metals always give away their s electrons first. So Fe2+ is going to be argon 3d6. Fe3+ would be 3d5. So once we've gotten rid of the s electrons, then we start getting rid of the d electrons. But with transition metals, and transition metals only, we get rid of the s electrons before the d electrons. Any questions on that? Yeah. Okay, so in electron configurations, we're talking about which electrons are lost when we start to ionize atoms. So in this case, a normal iron atom has 8 electrons in its valence shell. It has 2 in the s and 6 in the d. Okay. Now the d electrons are the ones that we just added electrons to, right? Because we're in the d block. But once it starts losing electrons, it doesn't lose electrons from its d subshell. Where it loses electrons are from the s. So normally, like if we were talking about, the example is, let's say O2 plus. O has an electron configuration that is 1s2, 2s2, 2p4. If it became O2 plus, it'd be 1s2, 2s2, 2p2. So it would just take away electrons from the ones that we just added. But that's not the case with transition metals. Transition metals take away from the s. All right, so last bit of exceptions. We're going to talk about F block. Electron configuration. So the periodic table you'll have on your exam and the one that's in the reader is actually different than the one that's up there. The only difference is whether you include La and actinium in the D block or you included the F block. In this case, you see La and AC, they're in the lactanides, right? So we would treat them as F block. But in the periodic table, in the reader and on your exam, it's just the opposite. They're going to have to be in the D block. So the reason this is because some elements, and I'll do some examples, like plutonium. So plutonium is, okay, 94, so atomic number 94. So if we were to do the electron configuration, we'd start with the nearest noble gas, Ru, Rn, radon. And then we'd fill up with our 7s2, and then 5f6, the way it's written right now. And then after that, we would start to fill up the D subblock. But another way we could write this, this is the one that you'll have on your exams, is 7s2, 6d1, 5f5. So that would be for this one right here. So as you can see, in this case what we would do is we're starting here, right? So we were at radon, we're trying to get to plutonium, Pu. So we'd start by filling up our 7s2. Then we'd fill up this one right here, it'd be our 6d1. And then after that, we'd move from 89 to 90 across to plutonium. The difference is between these two is one has actinium in the lactanide, 89 down there, while the other one, this one right here, has it in the D block. So because of the ambiguity, so it really depends on which atom you're talking about. Some of these in the lactanides have 1D, and some of them have none. They just are all F. Yeah. Here, I'm just going to rewrite it. So these are our two options right here. So in this case, plutonium The actual correct answer is the first one. So the first one happens to be right, but it would not be easy to predict on your own whether it has the 1D based on this periodic table, or whether it has no D when we use that periodic table. So you don't really know going in. So for that reason, you won't be asked on an exam to predict the electron configuration for something in the F block, because it'd be hard to know whether we're using this one or this one. But if we were to go through and do something on the other side, like antinium, then you would just assume they're all filled, so it wouldn't necessarily matter. What you may be expected to know, though, is if you knew the number of electrons, or if you had the electron configuration, could you be able to predict what lactonite you have? So let's do an example of that. So let's say you knew that the electron configuration was so this is the electron configuration for a lactonite. What we would do is just count the number of electrons, because we know how many electrons there are. There's xenon's number, so 54. There's 2 from the S, 10 from the D, and 0, or 10 from the F, 0 from the D. So we have a total of 66 electrons. So which lactonite has 66 electrons? Assuming it's neutral, which we're going to assume. Yeah, dy. So you were given the electron configuration, and you were able to predict that it's the electron configuration for dy. So this is a bit confusing, the differences in periodic table. You may want to take a look at it in your book, but just know that you won't need to predict the electron configuration. You'll just need to know how to go from an electron configuration to an atom. All right. Yes? Which one? Cool. That's good. So, that's a good question. I usually put it at the end. So I would put S, D, F. Okay, so now we're going to work through this. You guys should have worked on this or seen it from Brian. After this, we'll take a break. Okay, so let's start with sodium. Sodium, we'll start with the closest electron configuration, which is neon. Then we're going to fill up the S. There's only one, so it's just going to be 3s1. Okay, now for sulfur, we're going to do this like we did before, where we start with a neutral atom and then we'll add electrons. So sulfur is going to be neon, 3s2, 3p4. So I just went along, filled up the S, and I filled up the P. And now we have 2 extra electrons. So this is actually going to turn into neon, 3s2, 3p6. And what's this the electron configuration of? Yeah, argon. Okay, now for some chromium. So Cr. Okay, so that's in the 5th row in the transition metal, so number 40. So we're going to start with the closest one, krypton. And then we're going to fill up the 5s2. And then we're going to start with the D, so that's going to be 4d2. Okay, now for zinc. So zinc, we're going to start with the normal one, or we're going to start with the neutral one, because that's the easiest thing to do. So zinc is 30, so we're going to fill up, well, first we'll add our double gas. Then we're going to fill up 4s2. And then we're going to fill up all of 3d10. We moved all the way to the right, to the D block. This is zinc, though. We're looking for zinc plus, 2 plus. So that's going to be argon. Now, which electrons are we going to lose? The S1. So we're not even going to include it. So it's just going to be 3d10. All right, so the last one, or the second to last, is CM. This is not one you have to do on an exam, just so you know, because it's in the F block. So CM is 96, so we're going to start with radon. Oh, thank you. Yeah. Then we're going to fill up the S. This one happens to be that better off if we use this periodic table right here, because it does have one d orbital. So we're going to take this and write 61. So we got to go here. And then we're going to count across 1, 2, 3, 4, 5, 6, 7. So 7 electrons. So 5f7. Though you might have, the other way to write this would have been Rn 2 6 or 60 0. So I'm not even going to write 5f8. That's what you would have got if you used this periodic table. It happens to be that this one is different. All right, last one, then we'll have a break. What is the electron configuration of this? The easiest way to do it is count electrons. So xenon has 54. We have 2 from the S. And we have 11 from the F. So that's 13 plus 54 would be 67. So 67 electrons. Which one has 67 electrons? HO. Chromium. So any questions on this? All right, so you guys have an exam coming up, as you know. So I'll have a printout of what you'll want to know for the chapter.